Does anyone remember what we're going to talk about today? Kp, the equilibrium constant with respect to pressure, and its relationship with Kc, the equilibrium constant with respect to concentration. Yes, the goal of this lecture is to understand the formula and to be able to calculate one value from the other. When we have a reaction in which one or more substances is in the gas phase, we can write either a Kc expression or a Kp expression. It just depends on what information we know or what information we are trying to find. We can look at the Kc expression for our reaction, G cubed over EF squared, or the Kp expression for our reaction, G cubed over EF squared. In both cases, we have the same equilibrium expression, that products over reactants, and the coefficients are used as powers. The only thing that differs is that instead of having the concentration of G, we have the pressure of G. Likewise, we have the concentrations of E and F, and the pressures of E and F. Note also that we have a P as a subscript for Kp and C as a subscript for Kc. The subscript distinguish the two K values from each other because they will usually have different numerical values. The relationship between Kp and Kc is Kp, the equilibrium constant with respect to pressure, equal Kc times RT to the delta N. Why is that? To derive the mathematical relationship between these two values, we need to use the ideal gas law equation, but we're not going to show that here. If you're interested in the derivation, you can read the textbook and come to my office hours for questions. Sounds good? Great! Let's examine the equation. Note that RT is in parentheses, and so that delta N goes with everything inside those parentheses. R is our ideal gas constant, 0.08206 liters atmosphere per mole Kelvin. And our temperature, as usual, must be in the units of Kelvin. Delta N is the change in the moles of gas phase substances only, and is equal to moles of gaseous product minus moles of gaseous reactant. We will ignore solid, liquid, and aqueous solution because changing amounts of those do not significantly change the pressure. However, changing the moles of gas results in a very large change of pressures in some cases. So, we have to take that into consideration. Let's look at the decomposition reaction of dinitrogen tetroxide again. We have N2O4 going to 2NO2. The moles of product is 2 and the moles of reactant is 1, so delta N equals 2 minus 1 equals 1. Another example we looked at previously is the decomposition reaction of hydrogen peroxide. H2O2 yields O2 plus H2O. The mole of product is 1 and the moles of reactant is 2. Therefore, delta N equals -1. We can have positive or negative values for delta N depending on the specifics of our reaction. As I mentioned earlier, Kp and Kc will usually have a different value. Under what mathematical condition? We will have Kp equals Kc. Kp will equal Kc when delta N equals 0, because RT to the 0 power is equal to 1. Very good, Benjamin. Anytime we have delta N equals 0, the Kp value and the Kc value will be the same. For example, hydrogen gas plus iodine gas yielding hydrogen iodine gas. We have delta N equals 2 minus 2 equals 0. So in this case, the Kp of the reaction will be equal to the Kc of the reaction.